Hello everyone, welcome to this lecture of our series on quantum mechanics, and in this lecture we are going to learn very important and very beneficial lessons and formulas which comes frequently in our exams. So this is going to be very helpful for all of you and who are preparing for all India physics entrance exams. Okay, so in first of all I will discuss the things we have learned earlier in earlier lessons. So let me start, and don't forget to share with your friends who needs this. Okay, let me start. We have learned how failure of classical theory to explain black body spectrum have led to the quantum hypothesis of Max Planck, and how classical theories of Stefan Boltzmann's law and Wien displacement law have failed to explain the black body spectrum. And we have also learned how relation between volume and temperature of a black body, and how energy is discrete according to Max Planck's theory. We have also learned this is very important. Okay, we have also learned average energy of Planck oscillator and how energy is quantized. Black bodies consist of small quantum harmonic oscillators which resonate, also called resonators. Okay, and energy density of radiation according to Planck's theory, and wave nature of matter, de Broglie wavelength. This is also very important, and de Broglie wavelength in relativistic condition, and these are very important formulas of kinetic energy, momentum, and for thermal neutrons, de Broglie wavelength. And also we have learnt phase velocity and group velocity. So in today we going to learn about relation between phase velocity and group velocity. Phase velocity and group velocity can be related by this formula. Okay, this is very important. And for non-dispersive medium, group velocity is equal to phase velocity. Okay, always remember that. For non-dispersive medium in which d lambda of Vp is equal to 0 in non-dispersive medium, and normal dispersive medium, this is greater than 0. Therefore phase velocity becomes greater than group velocity. Okay, and anomalous dispersive medium, phase velocity is less than group velocity. Also remember that. And one very important experiment, and Compton effect. Compton effect is going to be very important, and very important to learn quantum mechanics. And this is the Compton shift delta lambda h by m naught c into 1 minus cos phi, and this Compton wavelength h by m naught c is called Compton wavelength. It has a value sometimes asked in exams, and this is the Compton wavelength 0.02426 degree Armstrong. Remember that, always remember. Okay, and relation between nu and nu dash sometimes asked in exams, and kinetic energy of recoiled electron. This also you can remember and understand. Okay, all right. Then Raman effect, and this is the Raman effect. In Raman effect, this is the Rayleigh spectrum, and this is the Stokes spectrum. In Stokes spectrum is less than the emitted wavelength or frequency, emitted energy is less than the absorbed frequency of radiation, and anti-Stokes energy of emitted wavelength or emitted energy is greater than absorbed energy. Okay, just remember that. And photoelectric effect. Photoelectric effect is given by Albert Einstein. He explains that if you emit a radiation in a metal, electron is ejected. It depends on the frequency of radiation. The velocity or kinetic energy of recoil electron is dependent on frequency, not intensity. And this is the very important formula: H nu equal to kinetic energy of recoil electron plus wave work function. This is work function. Work function is required to eject the electron from the metal, and this is stopping potential. This is some very important. And again, very important relation: if you need to convert electron volt to joule, you need to multiply with 1.6 into 10 to the power minus 19, and if you need to convert joule into electron volt, you need to divide by 1.6 into 10 to the power minus 19 charge of electron. Okay. Alright, then Heisenberg's uncertainty principle. This is very fundamental and very important in development of quantum mechanics. There are three types of relations in uncertainty principle: between position and momentum, energy and time, and angular momentum and angle. Let's remember that. This is going to be very helpful and important. Okay. Then linear momentum of photon. Linear momentum of photon can be expressed like this. Okay, S cut k. Then comes wave function. Wave function is the very fundamental and very basic in the development of quantum theory. Schrödinger developed wave function. This is, we can define wave function like this in 3 dimensions with in accordance with time. Okay, there are 3 conditions to satisfy a wave function. Wave function psi should be finite, single valued and continuous everywhere. This is the first condition, and the first derivative of psi should be continuous everywhere in space. This is the second condition, and third condition, psi should be square integrable, that is probability must be equal to 1. Okay, that is the square integrable. This finite, bound state and a scattering state, that is we have entered into the very fundamental and starting point of quantum mechanics. Bound state and scattering state. What is bound state? Bound state is bounded in a particular region. Okay, here energy is less than the given potential of that system. Okay, energy is less than the potential of that system, so that wave function is bounded in a particular region. We have this diagram like that. It is bounded, and at plus minus infinity wave function must be 0. That is normalization condition. Okay, scattering state. In scattering state, energy must be greater than the potential of that system. so that wave function is oscillating throughout entire space to minus infinity to plus infinity. This is the scattering state. Okay, in most of the systems in quantum theory we take bound states, and normalization condition is that square integrable, that is the probability is equal to 1. This is the normalized wave function. We have showed it like this in this diagram. And scattering state, one thing to be remembered, scattering state can't be normalized. Okay, always remember that point. And operators are very fundamental in our understanding in the formulation of quantum mechanics. Linear operator, this linear operator have property, these two properties. This constant comes outside when this operated on this wave function, and when this operator operates, linear operator operates on this two wave functions, then distributed like this. Okay, distributive property. And Hamiltonian operator, this is Hamiltonian operator, conjugate and transpose at the same time. Okay, this is dagger, conjugate and transpose at the same time. We will be using this Hermitian operator most of the time. This is the Hermitian operator, and if we use dagger, then wave function, this is the Hermitian, so it's becomes like this. Okay, a dagger is equal to a. This is the projection operator, and a square is equal to a. These two properties of projection operator. Unitary operator, a dagger is equal to a inverse. We can also define like this. And parity operator, when parity operator operates on a wave function, it's for symmetric potential we get two conditions. One is even parity and other is odd parity. In even parity, wave function is symmetric, and in odd parity, when you get odd parity, wave function must be antisymmetric. In this condition, whenever potential is symmetric, we will get symmetric and antisymmetric wave function. This is very important. And conditions to be quantum mechanical operator, this is going to be very important. Hermitian, first condition, it should be linear and should correspond to physical observable. Operators to be correspond to physical observable. Okay, this is momentum operator, it is Hermitian, and these are the Hermitian and anti-Hermitian operators. You can remember most of the time asked in exams. And ddx is anti-Hermitian, ddx is Hermitian, and it is d square by dx square is Hermitian. Okay, remember this. Properties of Hermitian conjugate, yes, it's very important. Double dagger, whenever you use comes, it's going to come operator, and this is the second, it's okay. This is also very important, and remember this. This is the distributive property, and whenever dagger is applied on multiplied operators, it's in reverse direction, it's all reversed. Okay, remember this. Even operator commutes with parity, this is very important. This is the even operator. We have let that A is a even operator, so it's going to be commute with parity. and odd operators anti-commutes with parity. This is also remember this. Okay, this is Heisenberg equation of motion. Most of the times we use this in formulation of quantum mechanics, and whenever this parity is conserved, whenever parity commutes with Hamiltonian, and the parity always independent of time, so it's going to be 0, differentiation going to be 0, and whenever parity commutes with Hamiltonian, then parity is constant of motion, it is conserved. Then remember this. Okay, parity is constant of motion, it is conserved, so wave function must be symmetric and anti-symmetric. Okay, and this is the condition. So thanks for joining in this episode, in this lecture. So more lectures are coming up, so share this video with your friends who need this and who are preparing for these exams, and this is going to be very beneficial for you. So thank you for joining.